In the last video we have done the simulation for the CMOS inverter, and we have done the transient analysis, and we have calculated the delay and that and all. And now in this video what we do is we will be doing the DC analysis, and we will be calculating the noise margin. So for that what I do is I will be going with the edit, and I will select my DC on the x-axis. So this is my DC source that I will be see from the 0 to 1 volt, and the step size will be this much. I will be keeping this one and give it OK. So the DC analysis is this one, and now I will be plotting my y-axis here. So even I can plot the x value also. This is what my output, and what I do is let me simulate it. Control R, we can do the simulation. So this is what the transfer characteristics for the CMOS inverter. So from these characteristics what we do is we have to calculate the noise margin. So when we are calculating the performance for the CMOS inverter through the noise margin, what we do is we have to identify the unity gain points. So this is what my transfer characteristics on which I have to identify the unity gain point, where exactly the slope of the Butler curve is equal to -1. So what I do is whatever the waveform that I get, I have to do the derivative so that I will be getting a slope. That graph I am going to plot it now. So the procedure to plot that graph is, so what I do is I will be going with the calculations and calculator. Let me select that. So let me set. It's already open. Right. So let me close. Yes. So for that what I do is I will be going to select calculator, launch the calculator, and I will be selecting the option derivative, right? So I will give double click, and the signal for which I am going to do the derivative, that signal I have to select it through the input signal that I have to select it. So this is the signal, output signal for which like I wanted to do the derivative, so that's why I have to select this one and get this one, and after that I have to go with add, so that the derivative of the by signal, derivative of the output signal will give the equation. So that equation what I do is I'll just copy equation or expression, I'll copy, and in the SDL window I'll copy the expression as it is, and now I'll do the simulation once again. Control R, so that I will do the simulation once again. Now the simulation not only for the output, I do the simulation for the derivative of the signal also. So let me select the waveform. So let me run again. So two waveforms will be visible now. So let me ungroup them. So this is the derivative of the first signal. So through this derivative signal I will be observing the unity gain points where exactly we have it on the transfer characteristics. So what I do is I will take a cursor, and I will be keeping my cursor. So I will be having, so you can see the slope of the Butler curve over here, -6, and now I'll move, and I'll move, and I'll move. So exactly this is the point. Yes, so it's nearby, right? Where I have the slope is around -1 around. So this will be the x value, and this will be the y value. Means this is the unity gain point, will have the input of this much and output of this much. So now what I do is I will be going with the explanation now. So from this, let me plot that where exactly I have the output transfer characteristics I got, and in derivative of the signal I got, on which so unity gain point already identified. This is what the unity gain point where I got the slope equal to -1, exactly here also I will get the slope equal to -1. So slope equal to 1 means this graph when it touches the -1, this is exactly 1 -1 we have. So where it touches the -1, the x value we have to project, and the same x value we have to take it for this graph also, and there exactly the at x value of that the corresponding y value. So this will be your v output. So this will be considered as a v input. So this will be one combination for the given v input. I got the v output. So now this v input is considered as the minimum. I consider as the v input low. So for the input low of the particular input signal at the unity gain point, I will be getting VOH. Means input when it is low, I will be getting V output high. So VOL, VIL and VOH, the two combinations I will get it. So if you see this one, the two combinations over here, so VOH and VIL. So this point and this point, these two values that we will get it from the unity gain point of the particular curve. So if I see that the values over here, it is 478. Yes, so this is what my 478 is on the x-axis. This is 478. So my V input low equal to 478, and the corresponding y value is 987. Corresponding y value is 987. So corresponding y value is 987, right? So this one will be treated as low value of the input, and this one will be treated as high value of the output, right? VOH and VOL will be calculated. VOH will be 987 millivolts and the VIL will be the 478 millivolts. So these 2 points we got it from the unity gain point of this one. In the similar way, what I do it, I will be taking another 2 combinations again. So this will be another 2 combinations where I get a -1 slope. I will be taking -1 slope again. Yes, so nearby I'll get the slope equal to -1. So this x value and this y value I have to take it. So what I do is I will be taking the two values 514. So 514 will be the x value, 514 will be the x value 514. So this is around the 514 exactly on the projection. So there will be y value I have to take it. So this one will be treated as VOL, output low value, and this one will be treated as V input high value. So input low value, input high value, output low value, output high value. So there will be 2 points that I have to highlight. This will be one unity gain point, this will be another unity gain point. So from the two unity gain points, what we do is I will be taking VOH, output high value and input low value. From this point, input high value and output low values, that I have to take the 4 combinations. That 4 combinations, that what I got it is so 13.2 milli. So this will be around 13.2 milli. So that I will be substituting over here 13.2 milli. From this, the range where we got it, VOH minus VIH, that I will be treated as a noise margin high. Noise margin high. Noise margin high. So if I do the calculation of the noise margin is around 987 minus 540 millivolts, it will be around 473. So I got the strength of the noise margin at a high level. So this one will be 473 millivolts. Yes, in the similar way for this one, I got BIL maximum is 478 millivolts minus BOL maximum is 13 millivolts. So this will be the strength. So from this, so the noise margin at a high level, this one we got it around 465 millivolts, right? So this much noise, even though it's added, it can transfer the data from here to here at a high level. And if it is at low level, this much noise, even though added also, it can transfer the data even at high level or no level. That much noise is considered as a noise margin for the inverter circuit which we have designed. Yes. So if you do the changes across the length and width of the transistors, we can change the noise margin. And there are multiple parameters through which the noise margin we do. For that we can do the parameter analysis also. So what we do is, finally we are achieving and we are expecting to achieve the maximum noise margin, where that logic 1 has to go as it is as a logic 1, logic low has to go as it is as a logic low. So if the logic high goes as a logic low, that will be a logic failure. So for that, to avoid them as maximum as possible, the noise margin we have to get it for the design circuit.